Welcome. Today we are going to study the reverse characteristics of a Zener diode. Today's class will be a practical class. Before that, we'll just take up what are the important things required. Well, the semiconductor device that we are going to require is a Zener diode. In our case, it will be 1N4739. The power dissipation or the power is 500 milliwatts. It is 0.5 watts. The Zener voltage is 9.1 volt and it can be seen from the data sheet of 1N4739. Maximum Zener current can be calculated from this particular formula where we know the maximum power and we also know the Zener voltage. Hence the calculation of Zener current, the maximum Zener current is easy, and in this case it is 54 milliampere. Now let us talk about the apparatus required. We would require a 12 volt DC regulated power supply. Using is a little bit different. And then we would require a R1 potentiometer. Here we are using 10 kilo ohms, 1 watt, 3 watt. Then we will be using 2 voltmeters. One will be used as voltmeter and another ammeter and wishboard. Now let us see how to determine the current limiting resistor while conducting the study on reverse biasing of a Zener diode. In order to do that, we need to arrange the components in this fashion, where on the left hand side you have B1, which is the 12 volt source, and on the right hand section you can see we have ammeters, we have voltmeters, we have Zener diode, one current limiting resistor R1, and a variable potentiometer which is directly connected across the source so that we can use it as a variable source. Now the two fixed terminals of the potentiometer is directly connected across the source, and the middle terminal is usually connected to the current limiting resistance, and the current limiting resistance other end is connected to the ammeter, and the other end of the ammeter is connected to the reversely connected Zener diode. Here the Zener diode is of 9.1 volts, and the voltmeter is connected directly across the Zener diode. Now, how to find out the current limiting resistor? Now, one thing we have to understand here is when the input voltage, that is V1, is at its peak, the current flowing through the circuit should not cross the maximum current handling capacity of the Zener diode. So in order to do that, what we have to do is we have to apply KVL into this particular circuit. Now when we apply KVL into this particular circuit, we know that in case of KVL, the input voltage is equal to the individual summation of the individual potential drops. So here the input voltage is B1 and the current flowing through the circuit is IZ. So the IZ is flowing through R1 and the Zener voltage is VZ, which is across it. So applying KVL, the input voltage will be the summation of the potential drops. Hence B1 is equal to IZ into RZ plus VZ. Now from rearranging this particular term, we can find out the expression for RZ, and then we'll be able to get the value of the current limiting resistor. Now we can see from here that after rearranging, we have got RZ equal to B1 minus VZ divided by IZ. Now if we consider the input voltage to be maximum, then it is 12 volt, and the Zener voltage definitely will be 9.1 volt divided by the maximum current that was already calculated previously, that is the maximum current handling capacity of the Zener diode, which is 54 milliampere. So computing this, we can get the value for RZ. Now if we carefully calculate this, we'll get around 53.70 ohms, and since 53.70 ohms is not practically available, we can approximate that into 56 ohms. So now let's see how it is practically done. Here we are using a regulated power supply. You can see we have a regulated power supply which is having plus 12 volt and a common which is actually the negative one. See, this is the negative one and this is the positive 12 volt. Now that particular wire is now being taken to the breadboard. We'll take that to the breadboard and put it somewhere. Okay, now we are putting this on the breadboard. This is the positive line, and then we will use the negative line here. It is the common line, and again we will connect that to the bottom of the breadboard. Now you can see the bottom of the breadboard is actually horizontally connected and the upper one is vertically connected. Now what we are going to do right now is we have to make this into a variable power supply. So in order to do that, we will use a potentiometer. Now this is the potentiometer. You can see this is the potentiometer, and the bottom you can see it is 10 kilo ohms and it is 1 watt. Now these are the two fixed ends and this one is the middle one. Now let us try to connect one of the fixed end with, you can see I'm trying to connect one of the fixed end to the positive supply, that is 12 volt, right, and the other one, the other fixed end, I'm going to connect that to the, yes, the negative one. Now the middle one is actually will provide us the variable voltage. Now if we turn the shaft, the middle terminal will provide us the variable voltage which will vary from 0 to the maximum voltage that is given by the power supply. It is approximately 12. Now we will take the middle one and put that onto any space on the breadboard. Here I am putting that into any location on the breadboard. Now my target would now be to connect a emitter between the current limiting resistance. So before doing that, we'll have to connect the current limiting resistor. Now since we need to have a 56 ohms resistor, but in my case I'm having 100 ohms resistor. So what I'm going to do is I'm going to connect 200 ohms resistor in parallel. So that will give, the parallel combination will give the value of the resistor as 50 ohms. So applying 50 ohms, I will be able to limit the current which will flow through the Zener diode. Now after connecting the 200 ohms in parallel, what I'm going to do right now is I'm going to use one of the digital multimeter as current meter. So first of all, I would try to rotate the dial in such a manner that it is turned towards 200 milliampere. Here we can see the dial has been turned towards 200 milliampere, and this is the emitter part. This is the DC emitter section. Now I'm just giving a small marking so that you can very well see where it is pointing right now. It is pointing towards 200 milliamperes, and this particular range is DC ampere range. Okay. Now what we'll do is we'll take the positive terminal of this here and we'll connect that to the other end of the current limiting resistor. See, what I'm doing is I'm connecting it to the other end of the current limiting resistance. Now the negative terminal of the emitter has to be connected. Again, take it to any location on the breadboard. Right. Now what I what we are going to do right now is we are going to connect the Zener diode in the reverse fashion here. Connect between the negative terminal of the emitter and between the common terminal of the power supply. So what I'm going to do is, right now take the Zener diode here. I have the Zener diode in my hand. I'm connecting the inside to the other end of the emitter. Here you can see the inside, which has been marked using black ring. You can see the black ring is actually the inside. Yes, if you can see it now, you can see it clearly. The black side is connected to the other end of the emitter, right, and the P side has been connected to the ground. Now what we are going to do is we are going to take another voltmeter which will act as a voltmeter here, DC voltmeter, and the dial has been rotated towards 20, as we can see from the first of all. What we will do is we will take the negative or the common terminal of the voltmeter and connect it to the common terminal, and we will take the positive terminal of the voltmeter and connect that across the Zener diode. So the voltmeter is completely connected across the Zener diode. Now the circuit diagram is complete, and we'll now switch on the power supply. So you can see it is presently showing some voltage and current. What we'll do is we'll first rotate the potentiometer and take it towards 0. Now what we are going to do right now is we are going to slowly increase the voltage, and you can see the voltage is getting increased, but we still do not have any current flowing through the Zener, since it is still in the non-conducting mode. And once it reaches very close to the Zener diode voltage, it will slowly enter into the breakdown region, and the current will start increasing. And now you can see the current is increasing very rapidly, and the voltage across the Zener diode is almost fixed. So this is how we can actually study the reverse characteristics of a Zener diode. Now since our Zener diode's voltage was 9.1 volts, and hence the current started to increase through the Zener diode when the voltage across it crossed 9.1 volt. Now if we record the Zener voltage versus Zener current, we can get the reverse characteristics as it is seen in this particular diagram. We can see we have taken both the voltages. These are the reverse voltage and the reverse current, and hence it has been plotted in the third quadrant, where the reverse voltage has been taken as negative and the reverse current has been taken as negative also. Now in this case, when the input voltage crosses 9.1, we can very well see that the current increases slightly, and when it reaches the breakdown region, the current rapidly increases through the Zener diode. But the voltage across the Zener diode tends to keep constant. It hovers around 9.1 to 9.3 volts. So this property of the Zener diode helps us to make voltage regulators. I hope you have seen how the reverse characteristics of a Zener diode can be studied, and we can also see the reverse characteristics shown here in the diagram. Thank you very much for watching this video.